In the last video, we looked at the general mechanism for a nucleophilic acyl substitution reaction when we are working with a basic or anionic nucleophile. In this video, we continue from that by going through an example problem of attacking a specific situation where we have a nucleophilic acyl substitution reaction under basic or anionic conditions. So we're going to go through how do we recognize that reaction and how do we apply that general mechanism that we learned in the last video toward this specific example of saponification, which by the way stands for soap making. And at the end of this video, after we've gone through the mechanism, I'm going to explain how this particular reaction qualifies as a so-called soap making or saponification reaction. So let's go ahead and take a look at this specific example problem. And in this problem, what we are going to do is write out the complete mechanism showing how we go from reactant to predicted product of the following reaction, where we are going to start in this reaction with a ester in this particular reactant. And we'll go to make our carbon chain here. And if we wanted to determine the name for this particular molecule, what we would need to do is to come up with the name. We name the O-alkyl group as the first part of the name. And so therefore the first part of the name of this molecule will be methyl. And then the last part of the name is an alkanoate, where the alkanoate part of the name refers to this full group, including the carbonyl and how many carbons it is in it and whatever branches comes off of it. This is a linear chain with no branches. Starting here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would be methyl decanoate as the full name for this. So methyl decanoate is reacting in this particular reaction with sodium hydroxide in water. So you can go ahead and hit pause and try to work through the mechanism for this on your own, using the general mechanism that we looked at in the last video as your template. See what you get to as the answer, and then hit play to determine whether you're on track or not with this problem. So to solve this problem, we recognize that our sodium hydroxide has a sodium cation complexed with a hydroxy anion, and hence that qualifies this reaction to fall under those basic or anionic nucleophile conditions. So that leads us down the road about what mechanism we want to pursue here for this nucleophilic acyl substitution reaction. We're pairing up a carboxylic acid derivative with a nucleophile, which leads us to say it's going to be nucleophilic acyl substitution when we have a nucleophile paired up with a carboxylic acid derivative, such as the ester we see here. In the first step of this basic reaction mechanism, what will happen is that since the hydroxide anion is a relatively strong anionic nucleophile, it is going to directly attack the carbonyl group of our methyl decanoate. So I'm just redrawing our methyl decanoate here. I'm going to double check that I have the right number of carbons in the chain here before I go on. 1, 2, 3, 4, 5, 6, 7, 8. Adding a couple more, 9, 10, to give us methyl decanoate. And the hydroxide anion is the reactive portion of the sodium hydroxide. The sodium there, cation, is just acting as a spectator. So what's going to happen here is that our anionic nucleophile comes in and directly attacks the electrophilic carbonyl carbon here. So we show the lone pair of electrons from the hydroxy group coming in, attacking that electrophilic, positively polarized carbonyl carbon. That is going to force the electrons from the pi bond up onto the oxygen like so to give us our intermediate. So I'm going to go ahead and make my intermediate, which is my 10 carbon chain here, directly bonded to oxygen anion. There is our oxygen anion, directly bonded as well to our O-methyl group. And also, now that we formed that new covalent bond to the hydroxy group, we have this OH group here as well. So we have our 10 carbon chain, and the carbon that was the carbonyl right here, and the starting material is now this carbon right here in our product. We've gone from a trigonal planar starting material to a tetrahedral product of this reaction step here. And so this step is what we would have labeled in our earlier general mechanism as the first step being the nucleophile, which is anionic, attacks the positively polarized carbonyl. And now, following our general mechanism that we looked at in the last video, the second step of this reaction mechanism is that the carbonyl reforms as the leaving group leaves. And bear in mind, the leaving group is always, if we look back at our starting material, the leaving group is always what the carbonyl group was directly bonded to, other than the carbonyl or the other carbon. So the leaving group here is definitely this O-alkyl group that I'm circling in my methyl decanoate structure in the upper left corner. That is going to be our leaving group because that is the heteroatom, and whatever it's bonded to, that heteroatom that was directly connected to the carbonyl there. So that's what's going to act as our leaving group. And so in this business about the carbonyl reforming as the leaving group leaves, we keep in mind that our leaving group is that O-alkyl group. So that O-alkyl group is what I'm going to break away, showing my bright green electron pushing arrow there to indicate the electrons go with the oxygen atom because the oxygen is the more electronegative of the two atoms in this bond. So that's going to create a methoxide anion, OCH3 minus. And as well, the other thing that happens simultaneously to that is the carbonyl group reforms. So I showed that lone pair of electrons coming down to remake the carbonyl group. And that's going to give us a carboxylic acid product. So let's go ahead and make that carboxylic acid product out of this. Adding in my 10 carbon chain, like so. And now that we have a carboxylic acid product, we've reached the end of our general mechanism for nucleophilic acyl substitution under basic conditions. With this particular reaction mixture, there is one additional thing though that you need to think about here, which is you've created a carboxylic acid product, the key term I'm emphasizing there being an acid product, and it is present with sodium hydroxide, a relatively strong base. And so what happens now is actually another reaction that goes beyond nucleophilic acyl substitution itself, where when we have a carboxylic acid present in a base, we have to think back to our chapter on carboxylic acids, remembering that carboxylic acids, being that they are relatively acidic, are going to end up getting deprotonated. So this part that I'm putting in a box here, where we're going to show the deprotonation of the carboxylic acid, is just a general acid-base reaction. This is beyond the nucleophilic acyl substitution itself, where the nucleophilic acyl substitution was just these steps 1 and 2 here. This was all our nucleophilic acyl substitution. But due to the conditions under which this product is subjected, being that the conditions are basic, that carboxylic acid proton, as we learned in our chapter on carboxylic acids, can be easily lost by reaction with a base. That will force the oxygen-hydrogen bond to break and the electrons to go onto the oxygen, giving us as the product we would actually observe in the reaction flask by mixing sodium hydroxide with our ester to give a carboxylic acid product. What we actually observe as the very final product is going to be a deprotonated carboxylic acid, because when you throw a carboxylic acid into a basic environment, it is going to lose that carboxylic acid acidic proton. So we still have our 10 carbon chain here. And I need to add a couple more carbons onto that to make sure it is a 10 carbon chain there and that I haven't deleted any along the way. Like so. So now we have our anion in our final product there. And that anion is attracted to any cations that are present in the mixture. And we had a cationic sodium to start with. So this would actually form a complex with sodium to give sodium plus, oxygen minus there. And we could come up with a name for that based on our knowledge from the carboxylic acid chapter, which would be sodium decanoate for that deprotonated carboxylic acid. And now this brings us to the reason why this particular reaction is referred to as a saponification reaction. Saponification refers to the making of soap. And when we talk about the making of soap, or saponification, and we think about what soap does and what the desired features of soap are, soap is aimed at being a way of dissolving or washing away oils and grease. That is the purpose of when you're using soap to do your dishes, for example. If they have a greasy residue on them, the soap will enable you to wash away that greasy residue. So why do we call this soap making, and why is this useful in creating soaps? Well, the reason this is called a soap making or saponification reaction is if we have a long chain alkyl group here, this long alkyl chain, which in many cases is not just 10 carbons, but more like 20 carbons, the long alkyl chain is going to be very hydrophobic. Instead of liking water, it hates water. It's hydrophobic because, keep in mind, like attracts like, or like dissolves like. This is not very water-like at all. Instead, it's the opposite end of the polarity spectrum. It's very nonpolar, so therefore it's hydrophobic, and instead it's referred to as lipophilic. Lipids are very nonpolar fatty molecules, and so since this chain itself is a very nonpolar chain, that makes it very lipid-loving. And hence, it is going to act to dissolve and wash away the fats and greasy molecules that are associated with your hands or with plates or whatever else you might be trying to clean. On the other hand, this portion of the molecule that I'm highlighting here, the carbonyl group, where we have also a deprotonated oxygen there, is the opposite. It is very hydrophilic. It loves water because it's quite polar with that negative formal charge there, and lipophobic. It is not going to interact very well with lipids, with fats. And so what we end up with here is a molecule that has two distinct portions of the molecule. One that is very fat-loving, one that is very water-loving. We refer to this type of molecule as being amphiphilic. Amphiphilic means that it has portions of the molecule that are water-loving, lipid-hating, and portions of the molecule that are the opposite, water-hating, lipid-loving. So amphiphilic molecules are molecules with both lipophilic and hydrophilic groups. So as a result, some part of the molecule loves everything is the way that we could think of this as. They are amphiphilic. Some portion of the molecule will be effective at interacting with and dissolving fats. That's our lipophilic tail here, as we call it. On the other hand, the so-called hydrophilic head, that carbonyl with the deprotonated oxygen additionally attached there of our carboxylic acid salt, enables it to interact well with water. And so that creates a molecule that is a very, very good detergent. And one of the ways that's able to act as a detergent is keeping in mind that like dissolves like, and we have these hydrophobic tails. When you have a bunch of molecules of the carboxylic acid salt, what will happen is that they form what's referred to as micelles, where micelles are spherical shapes with a hydrophobic lipophilic interior. And that hydrophobic interior is going to trap fats inside this spherical structure. And the sphere has a hydrophilic exterior, an exterior that's going to strongly associate with the water that's coming out of your faucet or whatever water you're using to wash the material. So it has a hydrophilic exterior. So the micelles form via the association of these carboxylic acid salts, and I'm not paying attention to how many carbons I have drawn in my chain here, so these are very, very likely an inconsistent number of carbons here, but the point is that these are going to arrange by large numbers of these coming in here and creating via all these hydrophobic tails coming in and forming the center part of the interior of the sphere that is fat-loving and will hence strongly associate with fats, whereas the exterior that I'm going to outline in blue here will be the outside of the micelle, the outside of the sphere, which is going to be water-loving, and hence, by organizing into these micelles, what the soap will do is it will end up ultimately trapping fats or greases inside the micelle, with then the water-loving portion assembling around the outside of this sphere and enabling water to carry this assembly away, therefore resulting in clean clothes, clean dishes, clean whatever else. And so as a result of this, you will commonly, if you look at the ingredient labels for common detergents and soaps, you will commonly see molecules that you would recognize the names of as being carboxylic acid salts, where you'll see the name of a metal as the first part of the name, and then the second part of the name will refer to some deprotonated carboxylic acid chain here that is a relatively long chain within the molecule. So that is why we refer to this as a saponification or soap making reaction, is that we're taking an ester starting material and we are, as a result of that reaction, creating as our final product a deprotonated carboxylic acid that has two distinct regions, a very lipophilic region and a very hydrophilic region, that will enable it to effectively dissolve greases and fats and therefore result in strong properties to clean materials.